Okay, hello everyone. I hope you are seeing the slides, and most importantly, you can hear what I'm saying. Can everyone hear me? Oh, okay, cool. Thank you so much, and Happy New Year, everyone. I hope 2021 will be a better year for everyone. Great to be with you again, catch up with everyone, and welcome to the new attendees. So let me just maximize this. Just let me know if the resolution is okay. Okay. Can everyone see the slides and the resolution? Everyone is happy with the res? Okay, cool. Okay, cool. Okay, so welcome to the first session of 2021. Let me just go through the agenda. I'll just do today, because obviously it's the start of the year, so we'll take it very lightly. So the idea is to just go through the concept, the stuff that we went through, and introduce new things that then next week we can try to bridge everything together. So we are now at a stage where we are ready to put things together that, in the past few months we've been learning them a little bit separately. So really well done to all of you and to the new attendees. The yellow stuff here, this is where we are. So to the ones that have been following, well done to all of you. As you can see, it's been a long journey to from here to having this thing done. So we are here now. It's possible that I will add an extra session here, because I'm not sure if I will be able to cover everything that I want to cover in 3 sessions. So we'll see how next week and week after goes. If needed, I'm more than happy to add 1 session, and I'm pretty sure that most of you will not mind to have 1 more extra session, and then we wrap up this the foundation module, and then we can start thinking about the next modules. In fact, I already have some ideas about the next module. So for now, I'm calling it Foundation Module 2. Maybe we'll change the name. So I think, given where we are in the foundation module, is probably the next logical step is probably to cover Lie theory in a little bit more in depth. So Lie groups and Lie algebra stuff. But to cover these guys, we need, because they have the manifold structure on them, smooth manifold stuff. So we need differential topology, and to work with differential topology, obviously we need to start from the basics, which is dealing with topology itself. What does a topology on a set mean? So we'll probably start here, and then have like few sessions on differential topology, and then spend most of the time on Lie theory, in particular Lie groups and Lie algebras. So that's the rough idea, because I think it really fits the current foundation module. Really, the logical step would be to cover Lie theory, I think. And then the functional analysis stuff, here I'm not sure. Maybe I could share some materials on like intro level stuff on complex analysis, so that way we can jump straight into functional analysis. But I'm also happy if people want to start from here. The basics obviously won't go too much. We only will only cover things that we need in order. And then the idea is then to, after that, we'll cover measure theory, also just what we need, to then come back again and revisit the quantum mechanical axioms, but in a proper way. As some of you, the ones who have been following the sessions, we are focused on finite dimensional Hilbert spaces. So there's a lot of limitations in terms of formulating the axioms of quantum mechanics with the thing. So we need a much more generalized axiomatic form that covers both finite dimensional and infinite dimensional Hilbert spaces. And for that, for infinite dimensional Hilbert spaces, you definitely need functional analysis and measure theory. Otherwise, you cannot, in a clean mathematical fashion, covers the stuff properly like we want. So yeah, anyways, just a rough idea for now, for the time being, okay? Let me just check the chat. Okay, so I see Amirik is excited about Lie theory. I'm also excited about it. It's a very, very beautiful theory. Hello, Soham. Should I actually, let me just pull Soham before I go, because I need someone to, in case my network connection goes. Let's see, Soham, if you are happy with it, of course. Okay, our friend Soham, Happy New Year.
Thank you. Happy New Year to you too.
Cool. Yeah, all good. Thank you so much for joining again. So Aditya is asking how many sessions. That's a good question. Huh? I might think about it. Maybe, say for example here, you probably maybe 2 or 3 sessions should be enough to cover, the basics of topology, and then here maybe another 3 or something, and then spend most of time here. Maybe 6 weeks, 6 to 8 weeks here. I think you should have a solid foundation on Lie theory. So we'll see. Maybe I can run a survey, or we just leave it like open-ended to see each topic. We'll see how people, whether people are struggling or they need what the thing. I mean, the thing is, it's very hard because Lie groups and Lie groups don't just have algebraic structure. So you need, to cover it properly. We really need, the differential structure really. So yeah. So in short, I'm not sure how many sessions. I guess it's something that we maybe I can send a survey afterwards. We can work it out. I might actually consult our friend Soham what he thinks about this. Perhaps. So Amir is saying perhaps for the orange boxes one could. Yes. Yes, we could do that. We could the thing. Yeah. We could spend a lot of time talking about symmetries and these things after this, because you will already have a lot of the language of symmetries here. So maybe concreteness really here on like how physicists deal with these things, like case studies and these things. And I might actually, I'm looking to invite a friend of mine. He's a bit reluctant. He's a physicist, or maybe Soham also. Could help with some of the physics side of stuff. Let's see.
Sure. Yeah.
We have a question.
That will be
fine. Probability. Okay. Yeah. Well, technically, this will be covered here in measure theory. So, because probability theory really, the language of it is measure theory. So yeah, we'll cover probability measures in there. But yeah, this is just to give you some sort of a flavor of what I'm thinking. But I'm open for suggestions really. So let's see. Looks like a lot of. Is there any tentative module dates for module 2? That's a very good question. It's the earliest is probably late summer, I would say, because we are in. I'm in the UK at the moment, and there's like a lockdown. And after the lockdown, I probably need 2 or 3 months to go and visit family and these things, like catch up with people. So probably the earliest is late summer. Possibly maybe autumn start. I don't know. Maybe I should send a survey also to see what's the start date for you guys. For the time being, in the gap after the foundation module, as I said in the last session, we will still be doing the fireside chats and these things. right? Just to keep people active, and I will still be sharing resources so you can, be refreshing and maybe, learn some stuff ahead of time. So yeah, it's just for me, I really need after this, especially after the lockdown, I need a bit of personal time for myself to just catch up. I'm sure most of you will be doing the same thing after the, whatever the geography you are located. So yeah, but I'll keep everyone posted on the community chat, and I will send emails. Okay, let's see. Is there any other question about this idea? No. Okay, so I guess we can move on. Yes. Okay, so let's go to part A. Part A is really, the idea is really to just go through the stuff that we went through in one of the sections, I'm not sure which, and then add new stuff, and then, you will have enough to then next week, because next week, then we will try to bring everything, bridge everything together. So it should be very interesting next week. Starting next week anyway. Before we start, I'll just make a remark, few remarks, in fact. So as I already mentioned, I've been mentioning it, this module is all about finite dimensional Hilbert spaces, but we know that finite dimensional Hilbert spaces are isomorphic to Cn. So from now on, when I say H, a Hilbert space, I will still use the notation H, just assume it's Cn that I'm talking about for some n greater than 0, right? And as you also know, the elements of n by n matrices, which, the set of n by n matrices is denoted like this. This is what we denoted. And they act as linear operators on Cn. Okay, and we also saw in one of the sections that, or the study materials or something, that any abstract linear operator acting on Cn can actually be represented as an element, as a matrix, as an n by n matrix, right? By fixing a basis, and then you can, construct a matrix representation of that. Okay, so matrices are really operators. Okay. And another thing that I've been repeating all the time, and apologies for those of you, is that for the guys, from a lot of you who are interested in quantum computing stuff, you don't want Cn for any n, you want n to be 2 to the k. So the dimension of the Hilbert space to be equals to 2 to the k, where k is the number of qubits that you are interested in. And to help make things easier, in some of the definitions, I will do the definitions in C2 because it's easier to see. And then obviously, most of the definitions, I will say, probably all of them will be generalized to any n. But to make it easier for you to see, it's easier to just, sometimes it's convenient to make a definition using C2 when we are dealing with the Hilbert space. And when we are dealing with the operators, to do the definitions in M2 of C to make it easy for you guys to see. Okay. And finally, do you remember this? The general linear group, which is the set of the group of all invertible matrices, elements of Mn of C. So whenever you see me saying a matrix, an operator belongs to this, I'm just saving myself having to say, because over the next coming sessions, we will often deal with invertible matrices. So instead of me saying, let A be an invertible matrix or, whatever, I will just say it's an element of this. And, or you will automatically insert, okay, yeah, invertible matrix, okay? So you will see what I mean in one of the examples. Okay, so let's start from the basics. Just as I was saying, we will use M2 of C whenever convenient, just to make things easier to see. Okay, so giving an element A in 2x2 matrix, the conjugate of that matrix is nothing more than just taking the conjugates of the entries. Okay, and this is like complex numbers 101. I'm pretty sure you all know this. The only thing I want to say is that in terms of notation, not the least because the study material is written by a mathematician, Mathematicians don't use star to denote the conjugate. They use a bar. So the individual entries will have like this, and so the matrix in the thing, you will mathematicians would write this as opposed to star. We are using star because this is what physicists use. Okay, and obviously these the definition can be extended to any n. Okay, and you can see these 12 examples here. I hope I didn't make any typo, but this is like a kindergarten stuff. I'm pretty sure you all know this, so I'll move on. And now we get to conjugate transpose. We also already covered this before, but I'm just refreshing because I know it's a new year. So the conjugate transpose is nothing more than taking the transpose of the matrix and then conjugating it. So that's essentially the transpose and then conjugating the entries of the elements of the transpose. Okay, now very important. Physicists write a dagger. Mathematicians write star. So in the study materials that I will reference, when you see star, it means a dagger. Okay, because the book is written by a mathematician or by two mathematicians. Okay, and again, this definition also can be generalized to n by n, to any n by n matrix. And some of you already seen, those who attended the matrix algebra section or whatever we covered before already seen this. So I won't go through this. I hope I didn't make any typos, and thank you for those who've been helping me spot my own typos. I've, I think, broken the record, the Guinness record in my company for typo. They call me Mr. Typo now. So, okay. Before we go here, let me check if there is any question. I think there is no question because this is all easy stuff, good stuff. Okay, so Hermitian matrices is something that we didn't cover before. I remember I was saying to you guys, like, it's probably better to cover it in this section when we are talking about operators and the axiom. So a Hermitian matrix is nothing more than just a matrix that's equal to its own dagger. Okay, so here's a very easy thing. I'm pretty sure you know this answer, so I won't spend much of the time. But here's a very interesting proposition that I really encourage you to try to prove, that given any two n by n matrices, we are not assuming that they are Hermitian. You can get a Hermitian matrix through this. So A plus its dagger is Hermitian. That's the claim. And of A and its dagger, and the dagger with A are also Hermitian. Okay. And there's also another very interesting property is that if a Hermitian operator is invertible, then the inverse of it is Hermitian. So this is already telling you that not all Hermitian operators are invertible. Therefore, the set of Hermitian operators do not form a group. Okay, I'm pretty sure you already concluded this also. But this is also another very interesting property to say that a linear combination of two Hermitian operators is with the real entries is Hermitian. This is very interesting. You will see this in the Lie theory when we talk about Lie algebra stuff. This will become very, very interesting stuff. Okay, and it says that the final property says that if A is a Hermitian, then the main diagonal entries, which is these guys on the thing, are real numbers. Okay, so I really encourage you to try to prove this before looking at the reference study materials, especially with the toy stuff, with the M2 of C, this 2x2 matrices. Try to prove this with the thing. Just look at the thing and try to prove them. Very important, this convention here. Okay. Because we are dealing with finite dimensional Hilbert spaces, we will take the word self-adjoint to be equivalent to Hermitian. In other words, when we say we will take being self-adjoint operator to be the same as a Hermitian, this is true for finite dimensional Hilbert spaces. For infinite dimensional Hilbert spaces, you will see when we get to functional analysis, this is not true. a self-adjoint operator is Hermitian, but a Hermitian, the way in the mathematical sense, doesn't have to be self-adjoint. Okay, there's some subtlety that you will not be able to understand now until you have the language of functional analysis, because it requires talking about domains and all these other stuff that we simply don't have the language for this. But in the functional analysis, you will see it will become obvious that what self-adjoint and Hermitian might not be the same, do not coincide. They only coincide in definitions if the Hilbert space is finite dimensional, which is what this module is all about. So for that, when I say self-adjoint, I mean Hermitian. Okay, let me check the chat. There's no question, so cool. This is great. Another interesting thing, just for you guys to see that Hermitian matrices are very interesting. They are not boring. So we have the notion of a skew Hermitian matrix, which is equals to the additive inverse of its dagger. Okay, so if A equals minus A dagger, it's called skew Hermitian. And the term skew Hermitian, this is normally used by mathematicians. Physicists tend to use antisymmetric. Okay, so if you hear pick a book written by physicists and they say you see this especially in the quantum mechanical sense, dealing with the operators, they mean skew symmetric. They mean this. Okay, and here's a very interesting property. Also, the claim is this, that notice the signs has flipped. Remember before, for a Hermitian, you put plus, you get a Hermitian. Now, if you take the minus, so if you subtract with the dagger, you get a skew Hermitian. That's what the claim is saying. So again, I would leave it to you to prove that this is the case. And very interestingly, the linear combination of skew Hermitians with alpha and betas being real numbers is also skew symmetric. Okay, and this is very interesting. So it's so if you multiply a skew symmetric, a skew Hermitian matrix with I, where I is the unit, the imaginary unit. Sorry, I'm getting ahead of myself. So if A is Hermitian, you multiply it with the I, you get a skew Hermitian matrix. Okay, and if you do the same with a skew Hermitian, you get a Hermitian back. So the I multiplication by I takes you from Hermitian to skew Hermitian. This is very interesting. You will see this will become a very interesting property when we at some point when we deal with the commutators and these things. Okay, so let me check the chat. Okay, so again, I really I encourage you to try with not necessarily prove it for the general case of n by n, but even for 2 by 2 matrices, Okay, so now here's a theorem for some of you who have been following us. We call theorems things that we think really are very interesting, that are worthwhile calling theorem, and this is the case, I think. So it's telling you any n by n complex matrix can be decomposed, admits this decomposition. I'm pretty sure I didn't make any typos, but if that's the case, later on, please ping me, and I will buy you a beer next time we catch up in person. Okay, so this is very interesting. So it's saying that for any n by n complex matrix, you can that matrix can be written like this. This is a very interesting property. And the first half of the term, this term here, this is called the Hermitian part of A. And this one is called the skew Hermitian part of A. Okay. So now I have like a challenge for you, which is these famous matrices in M2 of C is for you guys to go and compute this, to see. So let's just plug in and see what you get. you will see. So Nikolai is saying better. It's yeah. Thank you, Soham. Yeah. So beta are real numbers. This is. I think you already noticed that because of this already. No, not that. This property that if you multiply either Hermitian or skew Hermitian with the imaginary parts, you will move them away. You will not preserve their property. Okay, so it will move you away to the other one. It will take you to the other one. Whereas if you multiply with the real numbers, so without the complex part, it maintains. It keeps it maintains the structure. Okay, so multiplication by real number does not break their structure. This is what this is telling you. I hope that makes sense. Yeah. Okay. I mean, these are all things that at home, take your time over the next coming days. Think about these things. This is how they get into the head. Okay. There's a duplicate here, so sorry for that. Another notion that I would like to go with you is the diagonal, the concept of diagonal matrix, which we already covered before, but I will just cover again because next week we will start. All these things will start to be packaged together to get interesting results that we are interested in. That's why I want to refresh you on these, so next week I don't have to talk about it. Okay. So apologies for those of you who already know this, but yeah, I will just in case. Okay, so next week when I come in, there are no surprises. So a diagonal matrix is nothing more than a matrix where all the non-diagonal entries, which means anything outside here, they are all zero. Okay, so that's what this condition means. I'm pretty sure you know this. Now, it doesn't mean a diagonal matrix doesn't mean all these guys need to be non-zero. There might be some of them that are zeros, yeah, but obviously you don't want all of them to be zero. That's why that's where they become interesting. Okay, so for example, this is a legitimate diagonal matrix. It has a zero here, but so what? It doesn't have zeros all the time. And obviously, by definition, the zero matrix could also be classed as diagonal because it has zeros all over the place. But it's like it's useless. What you want is the matrices that don't have zero in all of them at least. Okay, so I believe this proposition is something that we already covered in the previous session. So I will remind you again that if A and B are diagonal, then their product is also diagonal and they commute with each other. Okay, so I'll leave that as a homework challenge. I think you already done this in the previous section. And this one is also more of for you to scratch your head. So what I'm asking, because D is an operator, right? It's an operator. So the question is, what is the kernel as an operator? What is the kernel of D if the lambdas are all non-zero? Okay. And second, if there is at least, or let's say just one, if there is one lambda that's zero, what's the kernel of D? I think some of you already know the answer, but that's it's just for you to go and scratch your head and think about diagonal matrices. A very important definition here, I didn't bother to call it definition, but it's very important. You will see in the next session when we are talking about diagonalization and this stuff. So D is called real diagonal if all the entries are real numbers. Okay, so if it doesn't have any complex, any components that's complex. So all the components here are real. Okay, so they're real. They don't have the complex component. Okay. Okay, so let's see. Well, I didn't mean to say the zero matrix is useless. So apologies for the zero matrix. Yeah. What I mean is, in general, what you want is like, you don't want all of them to think, because this is where you can get interesting properties with it, right? Which you will find out next in the next coming sessions. So, is there any confusion somewhere in my notation? Lambda is the element of the diagonal. Yeah. Yeah, there is a confusion on the notation. Apologies for that. Yeah, so lambda is a element of the diagonal. I think I meant to give an example of a diagonal matrix with the lambdas on the thing. Yeah, so I should have probably used the these guys here, the thing. So yeah, I will correct the slide. Yeah, thanks for the thing. Apologies for that, for the notation, the confusion. I was meant to write D with the lambda as its components. I think I forgot during the time, because as you already know, it takes me about, I only start doing the slides about 1 hour or 2 hours before. So yeah, so lambda are diagonal, the elements of this. So just imagine the lambdas here on the thing. So yeah, sorry for that. I will correct the slides and upload the thing to make it easier for people to understand. Okay. Understood? Okay. Yeah, okay, cool. Yes, 1 hour before. Well, not necessarily 1 hour. I already have like a rough idea, so it takes me like a thing to have the idea, but the actual LaTeX typing stuff, just over 1 hour or so that I get the stuff done. So yeah, so you understand there is high chances of having typos all the time. So yeah. Okay. So let's move on. Now here's a lambda. Okay, so in here I've already written D with the lambda as its components. Okay, so here's a proposition for you where D written like this with the lambda as its diagonal components. The claim is D is invertible if and only if the lambda i's are all non-zero. Okay, I think you already proved this before in one of the sessions that we've done in the past. And the second claim is that the inverse of D is of this form. Okay, so I think this is like very easy. Also, you already done this in the previous session. So I'm just refreshing you again, because next week we will diagonal matrices will play a very important role in some of the results that we will be exploring. Okay. Check the chat. Oh, thank you, Barry. Yeah, and the LaTeX can be a bit of a pain, actually. Thank you. So now I have my excuse. If I have all typos, you now have a better understanding to why I get typos all the time. Especially on Fridays, I'm getting out of meetings, the last meetings in my company, so I can do the slides and these things. So yeah. And I really encourage you on the chat, if you see any typos like some of you have been doing, is really grateful. Aditya, thank you for the time for the previous typo where the thing that's already corrected. In fact, I don't think I corrected it. I corrected it on the chat, but I didn't update the slide. But that's fine, because that particular part of this thing is not something that you need for this foundation module. It's something that we will touch on functional analysis, and it's also minor. It's just instead of putting what was it, epsilon, I put kappa or something. So I switched the thing. Let's see. Okay. Let's come back to our friends, the unitary operators, okay? They will also play a very important role next week. So that's why I'm refreshing you. Obviously, we covered them in the context of unitary groups. So I'm refreshing you now. So if an n by n matrix is called unitary if it satisfies these properties. So the product of A with its dagger is the same as the product of its dagger and itself, and it's the equals to the identity. In other words, A dagger is the inverse of A. Okay, so it's called the same unitary, and you can see these guys here. This is like trivial stuff that you all know, I'm pretty sure. And now here's a very interesting construction. So if we have theta 1, theta 2 to theta n as real parameters, real numbers, we can construct this diagonal matrix where E is the Euler constant, right? This is something you all know, I'm pretty sure. So the question is U of written like this a unitary? And also another thing I want to is what is the U of 0 pi? It's right in front of you. That's the question. I'm pretty sure you know. Okay, I'll leave you to scratch your head around it. Okay. My screen has frozen. That's why I'm not able to move to the next slide. Sorry for that. Let me refresh. Sorry for that. I'm going back again. Where were we? We were here, I believe. Okay, I'll leave you to scratch your head on this. Yeah, so this is the only new thing that we are introducing today. I wanted to cover more today, but I thought, like, it's the first session. If necessary, I will add an extra session. Let's take it easy so you can go back, go home and over the next coming days, wrap your head around all these things and the previous stuff that we covered. Okay, so this is the concept of a similarity of two matrices. Okay, so let's fix an A, or let's A be an n by n matrix. So we say another matrix B is similar to A if there exists an S invertible. Remember I said this is where I needed that thing because I didn't want to write, there exists an invertible matrix S. So it's, it's much simpler to formally to just write it this way, because an invertible matrix is an element of this, okay? Sorry. Okay, so if there exists an invertible matrix or, an element of GLN of C such that this condition is satisfied, okay? And then we write this B, similar to A to denote the similarity, relationship similarity with between the matrix B and A, okay? And here's a proposition that I would also recommend you to try, which says that similarity relationship is an equivalence relationship in the set of n by n matrices, okay? What that means is that these properties here are true. So A is similar to itself for all A. So this is called a reflexive property. I don't think we covered the equivalence relations when we cover set theory, but this is this type of stuff that we will definitely cover in the advanced in the next module stuff when we are talking about topologies and these things. Okay, so here's a thing. This is very I'm pretty sure you can prove this even if it's just for the case of 2 by 2 matrices. Okay, so I'll leave this. This concept of similarity will become a very, very important thing next week, when we are talking about diagonalization and this type of stuff. So it's very important that you wrap your head around it. Okay. So As you can see, let me check the chat before we go to part B. This is really all we have in terms of what you need to carry. Next week, we will obviously cover more, and you start to see more things. So today I just decided to, to just take it easy, so you know what you should focus on before we before next week. Okay, so thank you. So, okay, let's go to part B just for comments on the Dirac notation. This is also very important because this is to do with the notation stuff. And in fact, I already I forgot to remove one of the bars here. The convention in physics. Sorry for that, but you can just remove. I'll explain this in a minute. Okay. So for those of you who in the previous session, I think we talked about the notation bra, which is essentially just a linear functional, or if you want to be mathematically correct, is just an element of the dual space, since we are talking about this the thing is frozen. Sorry again. Okay, so where was I? Yeah, we're talking about bras. Okay, so we've seen in the previous session that the bra is just a linear functional. Okay, the element of the dual space. By the way, one thing I forgot to say, this is just a notation stuff, but it might become very important, especially when you pick a book written by a physicist, because sometimes, especially in this in quantum stuff, you have a lot of books written by physicists. Physicists normally don't write the dual space. They will probably often have seen books where they write it as the H dagger, not to mistake it with the Hamiltonian, like with the H. This is the thing, the Hilbert space. So if you see the Hilbert space, the thing, they would write this, okay? And we saw that because of the Riesz representation theorem, every linear functional, or in other words, every every element of the dual space can be written as a bra, okay? So for those of you who don't know what we are talking about, if you watch the previous session, you will see how the bra is constructed out of the inner product, okay? So I recommend you to go back and watch the previous session to see how the bra is constructed from the inner product. And what the Riesz representation theorem says is that every linear functional can be written as a bra. Okay, so you will understand if you watch if you are struggling to understand this, you will understand if you watch the previous session. Okay, now another operator that I forgot to mention is this one. So if you have two cats, let's call them psi1 and psi2. We can construct another operator. I will call it kappa psi1, psi2, lack of imagination, that goes from H to itself. So it's an operator, and it's defined like this, okay? So you take, the operator acting on another cat, let's call that phi, is like this. You take the inner product of psi1 with phi, and then you multiply the results with the psi2, okay? And sorry for that, for this the notation. Remember last time we were saying that physicists decide to take one of these lines, so they only keep one. So I will correct these slides. I will remove this, so it will just stay one line here, which is, for a mathematician, this is just the inner product. But the physicists would see this as the bra acting on this on this cat here. Okay, for a mathematician, which I think is the simplest way to see this, just see this as the inner product of psi1 with the phi, and then the result, which is a complex number, you multiply with psi2. Okay, now physicists, instead of writing this, this is a bit ugly, frankly, this is what they write. So when you see physicists write this, What they mean is the operator, this operator here, okay? And when psi1 and psi2 are equal, which is in this case here, okay, this is what they call projection operator. So if you fix, for example, if you fix, say you fix an orthonormal basis, which is what's used in Hilbert spaces, you take the matrix representation of this, it will give you to the matrices that the physicists they construct, okay? So you will get the same thing as what, all these fancy calculations, the way that physicists construct the matrix, you will get that. You will get that out of this if you construct the matrix representation of this operator by fixing a particular basis, okay? So it's very important. So if you see physicists write this, they mean this formally. But obviously, in most courses, like this intro level stuff, especially dealing with finite dimensional Hilbert spaces, they would represent this in the matrix form. But in the abstract form is this. This is the thing. The matrix representation is the representation of this. Okay? So, yeah. Yeah, there's probably a typo somewhere. I myself, I'm very confused with the physicist notation, so apologies for that. Let's see what Barry, where's the, yeah, the physicist, yeah. Yeah, I'm silent because I'm trying to detect to see if I did myself. I don't think I did a typo. This is definitely a linear. It's a linear operator for sure. Yeah. The thing I was calling attention is just this thing here. I think the only thing I forgot is to remove one of these vertical lines, which is the convention by physicists. But anyway, you see it as it still is the same thing. It's just another abbreviation that they did, because in reality is the bra, this psi1 is acting on this ket, and then the result of that you multiply with psi2. Okay, I don't believe I made any typos, but I will double check and correct on the chat.
I think for the physicist notation, the psi2 and psi1 will be interchanged or something like that.
Ah, okay. So thanks for that.
Yeah.
Okay. So you see, even myself, I get confused with the physicist notation. That's why I would prefer the mathematician's notation. Is much more cleaner. But I don't know why physicists choose this. So yeah. But it's in general, this is the thing of this form is an operator, and you can build a matrix representation of that. It should give you what physicists construct the matrix. Okay. So, but I will double check again. Thank you for that, Soham, for the correction. Another very important thing I've seen a lot, especially in people in quantum computing. People coming from computer science background, they normally write this, they label the orthonormal basis, like 0, 1, blah, 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 to n minus 1, when they are dealing with the, this space, okay, the ortho of Cn, okay? So if you see this, they mean, this is the orthonormal basis. Obviously, we will use this in this session, in this module. In fact, this is notation able the thing with the 0, 1, blah, blah, blah. Okay. And to make the things even more complicated, this is where the Dirac notation becomes very like a minefield, because it becomes very contextual. Because physicists, some physicists at least, especially the ones working in particle physics, or I would say like quantum optics or this type of stuff, it's normally, Sohan can also correct me on this, please. They would write this to denote the states with, say, for example, n particles. Okay, so this one here, this will not be the basis, the one basis. This would be the state, representing some system with one particle. Okay, So you will see this a lot in, like, you know, in presentations, in webinar, and you will see it in conjunction with things like creation and annihilation operators, this type of stuff. So it's very important that before you interpret the Dirac notation, pause a minute and see who is writing it. Is it a computer scientist, you know, the thing, or is it a particle physicist, or the thing? And to just to put it into context, because it might mean different things, right? So yeah, just a word of caution there. Yeah. Thank you, Soham, for confirming that. Okay. But for us, we will stick with convention of using E, you know, E1 to the EN. Okay, so just a small comment on the Dirac notation. I hope I didn't miss any. I probably missed other convention of Dirac. The problem with the Dirac notation, you know, you start to get into rabbit hole, right? There is all sort of convention. Oh, you do this, and now you do. There are all sort of rules that become very confusing, especially if you are becoming from a mathematics background. This thing becomes very annoying for, like, it's like abuse of notation. You gain nothing really from a mathematician's point of view, anyway. But nevertheless, physics is like this. So, you know, so what shall we do? Okay, so let me move on. Sorry for that. And let's now go to, I want to make some comments on the axioms of quantum mechanics. Now, a friend of mine, someone convinced me maybe I should put that the regime, the stuff that we are actually, the quantum mechanics that we are actually trying to cover is the non-relativistic quantum mechanics. This is, I didn't want to add these details and these things because I think it doesn't matter. But, you know, for those of you, this essentially means that you know, we are ignoring so we are ignoring relativity. Okay, so this is what non-relativistic in a nutshell. This is what it means. Maybe physicists like Soham can step in and elaborate more, but it's not something I want to go in for now. But I was convinced to make a note here, so you know, most of the standard test books that you see in quantum mechanics are indeed dealing with the non-relativistic version of quantum mechanics. Okay, that doesn't take into account relativity. Okay, so these are like details that probably not worth mentioning here. Maybe in the advanced section, once we go through the, you know, in the revision of the quantum axiom, you know, the non-relativistic stuff. Okay. Now, Axiom One, already, for those of you who are joining us, you know, we already gone through this. So it says that the state of quantum systems, I will make a comment on this also. This friend also told me this might be a bit ambiguous. What do I mean with quantum system? Quantum mechanics is more fundamental. His criticism is that this makes it look like there are two types of systems in nature, right? There is the quantum system, there is classical. So his argument is that quantum mechanics is fundamental. You know, even there is no such a thing like you know, you have in his argument anyway, you know, everything is quantum mechanical. It's just at certain scale, you know, when the masses are large, you know, you don't notice the quantum mechanical effects. Okay, so in his point of view, when we say, you know, the states of quantum systems, this conveys the idea that, okay, you know, there is a quantum system, there are classical systems and these things, but in his view is that, you know, the reason quantum mechanics is more fundamental, okay, than classical. Okay, so maybe this is something Soham maybe can comment. So anyway, leaving that details apart, so the states of a system, so maybe I should have removed quantum system, but yeah, let's just keep it in the context, are modeled by normalized vectors on separable complex Hilbert spaces. Okay, we already know what separable complex Hilbert spaces are, and in fact, this my friend also called attention, he was right also, actually this is not quite right in a way, but we can ignore this for now because this is first of all, this is like what physicists call a pure state. Okay, so this is closer to truth in this thing when you are dealing with pure states. There is something called mixed states that we mentioned before, but we will not cover on this module. This is why we need to refine these axioms in the advanced module. Okay, but yeah. So anyway, this is axiom 1, which we already gone through because we already know what a normalized vectors are, what separable Hilbert spaces are. And axiom 2 tells us that the observables of quantum systems are modeled by self-adjoint operators on separable complex Hilbert spaces. Okay, and I claim is that we already know what axiom 2 is telling us. So observables are things that maybe this is where our friend Soham can help us also. So physicists call observable things that they can measure, like say for example the energy of a system, or as they call them the Hamiltonian. Okay, so what this axiom is telling us, these things, the modeling aspects of it are encoded. These things are encoded in self-adjoint operators. But because we are working in finite dimensional Hilbert spaces, you remember the convention that we did that we will call self-adjoint to Hermitian. It means that in our case, when we have systems being modeled with the finite dimensional Hilbert spaces, then the observables of the systems are encoded in Hermitian matrices. Okay, so we already know how the modeling. So we know how the state is encoded, and now we know how the stuff that you measure, the observables, the physical quantities, are encoded. Okay, so far we are in the kinematic aspects of the theory. Okay, so we will build on this next week. We will add another axiom to see how actually the state and this relate to each other. So that brings me to my recommendation. It's actually not this one. This is the study material. We'll come back to this because I really think this is now the time for you guys to have something supplementary, especially things to do with the physics. So you get the maths from me and discuss the mathematics of it, but you probably need to see like how working physicists deal with these things. And for that, I think there's this free course by Perimeter Institute. It's free, available. I will share the URL, or you can also just Google it and go through this URL. And the first 7 lectures of it are very, very good, especially in terms of this thing here called the operational framework. I think this will make it very easy for you to kind of, get into seeing, how in practice physicists deal with these things without worrying too much about, all this foundational stuff, which is not to say that those things are not important, but it's just more pragmatic, I think. And this is by Aggie Branchek, and it's, she discusses a lot of stuff that I think will be very, very useful, supplementary to the math side that you will be, getting from this side. So I really recommend this thing, and I will probably recommend it. Maybe start covering this after we go through all our stuff. Then it's much easier. But feel free also to watch, say, lecture 1, for example, to see how the operationalist framework is laid out by her and these things. Okay, so it's really great. Unfortunately, there's one downside with this. I found this site in terms of watching the stuff. The quality is not that good. They also enable the download. So I got in touch asking whether I could create a playlist. Obviously, I would give them credit. So it's easier for you guys on YouTube with the higher resolution, but unfortunately, that's not possible. So they don't want that. So you have to watch it from here. So, and I really recommend. It's very, very interesting content, especially in the context of this. There are other stuff. So there are this section here is covered by Agi Branchek. There is another person giving another that covers more things that I think is probably a little bit more advanced. Like, but these things here I think are is like the natural progression from after you go through this this module. Is probably the best, and you will see that the way the stuff, the mathematics, some of the mathematics will be maybe not covered the same in the same rigor as we've been doing on the thing, because after all, you know, this is a physics stuff. So, but nevertheless, I think you will be able to follow this, and you'll probably extract a lot more, especially from the the way the physicists deploy the mathematics from this from something like this. And I will keep checking out for more resources, especially on the physics side, that supplements the mathematical side. Okay, let me check. Okay, so I see a lot of interesting things on the chat. Relativistic, yeah. Thank you, Soham, for clarifying. So, the formalism. So yeah, to deal with the relativistic quantum mechanics, you really need much more sophisticated mathematical machinery. Okay, and even then, there are a lot of things that are not rigorously really the thing. So you have to kind of it's very hard. There's no way that we can cover these things. Okay. Finally, I don't see the chat. Sometimes it loads the thing. I only see few things on the chat, like the last few messages somehow. Maybe because I'm a presenter, so there's a limit I can see. Yeah, we will also cover, I think next week, actually, we might, no, not next week, the week after, we might cover some other stuff. I mean, sorry for that. I was being distracted on the message. I might add some extra stuff for you to help supplement the mathematics. And now, this is the thing. Since we are dealing with the finite dimensional stuff, this is the thing that I recommend. Really, it's this. I think there's a link where you can download this for free. I will share the link with you on a test file, so you can download. I cannot. Because I'm not sure if it's allowed, I cannot download it and put it on GitHub. Then I will probably get a takedown notice. But if you check the repository, I will. There will be a test file that will have a URL from where I know you can download this for free. Okay, so I will share that with you. Okay. Let's see. Yeah, there isn't really much more I can say. Soham, was there any particular question that I missed that I should have picked?
No, I think pretty much all the questions were answered.
Yeah.
I think the most questions were about the typo, and that was answered. So that's fine. Yeah.
Okay. Okay, well, does anyone else have any questions, not necessarily for the session, but for other the stuff that I shared before, or something else, or any other comment? I'll definitely on the thing. Let me go back again to the thing. The foundation module 2, why the thing. I would like to get, especially those of you guys, that attend regularly, to dictate what you want to cover. Okay. And these things, like the thing. So, and ideally, obviously, it's topics that I feel comfortable with. If not, one of my other colleagues will have to come in. So, and these are topics that I pretty much like, all these guys. So, okay, I see a question by Aditya. Yeah. One lecture or maybe half lecture on reading. I think I shared a book about proof writing. One of the reasons, especially, I would like to make a comment on this. One of the reasons that especially in this foundation module, I think there's hardly anything where I have written the thing, because I've worked you through proofs, because I think that would have taken the sessions very long. I'm not sure if we could do that. If I walk you through, step by step through the proofs, that will probably take us more than 1 hour, So, I'm not sure if everyone has time for me to walk everyone. And secondly, I think it's very important that, you yourself, you get into this thing of, feeling comfortable proving stuff yourself, and feel confidence. And as I said, sometimes, most of the times, there are different ways of proving something, so it's not like your proof is wrong, the other person, you might get to the same conclusion. The only difference is some proofs are much more elegant than the others. Okay. But yeah, I'm also happy to do that, to kind of, especially I'm like in advanced stuff here, because there are like very interesting results. I'm happy to walk you through the proofs, or even write my own version and these things and walk you through that. It's just people have to be available, right? Because walking through like step by step stuff, like going through that, the lectures will take too long. Yeah. Yes, Barry is right. It takes too long to become comfortable writing proofs. It's true. Yeah. Yeah. It's a practice. I mean, at the end of the day, it's like a practice. It's like, a lot of you on the audience are programmers, The more you write code, the better you become, right? So it's the same thing. The more you write proofs and these things, Even me, because, many years now, especially after switching to industry, I don't feel the necessity to, to be proving stuff and these things, like the thing. So, I might consider myself a bit rusty, if you know what I mean. But, as they say, if you you know how to ride a bicycle, you will always know how to ride a bicycle, right? It's saying you might be like a bit thing, but yeah, it takes practice, really. It takes practice. Yeah. And for those of you, inspiring to contribute to new knowledge, in quantum information or even in physics, it's really very important, to kind of feel comfortable with this, because this is how you prove stuff. You're not going to go there and say to someone, hey, I have a proof of this, this I have a hint, or there's the thing, people will say, okay, yeah, prove it. So yeah, George, that's a very nice line. A mathematician is a device that turns coffee into proofs. Yes, it's true. Yeah. I mean, one of the things that I will also look to do, maybe we could have particular sessions on proof writing. That could also be like a supplementary thing, like some particular sessions in parallel or something, or before these guys. I'm really open for that. Or you yourself, you could organize yourself with like a study group, a community for you, those who have time. You could come together and have like a session together. So at the TSA, maybe one proof every lecture we could go into. So you mean you presenting a proof? Well, I'm more than happy to pull you if you think people want to. Yeah, that's fine. We can do that. We can do that, and we don't need to record it if you want. Maybe this could be like as part of the after session. We can have another session that's not recorded. That's maybe you feel comfortable. Then go on the thing on the private. Not everyone seeing you walking through the proofs. If you the thing, it's fine. We can do that also. You mean I walk you through the proofs? Yeah, I'm happy with that. Ideally, I would feel more happy to walk you through like interesting proofs, but not like these boring proofs, like proofs of very important theorems. Like those are more interesting than going through like other stuff that other people it's already been proven, right? I mean, it's like easily provable. It's just a matter of patience and these things. Yes. So. Just out of curiosity, for those of you who are still around, who of you are planning to follow a career in physics or quantum information and these things, or at least type 1 if for physics, 0 for quantum information? Okay, well, yeah, 1 plus 0 for both. Yes, indeed, I forgot that. Because you can follow both. It's true. Okay. Yeah. Yeah, I mean, these are like open fields, really. Like there's so much. This is the thing. I always say to you guys, editing. There's so much to be done. It's like, don't feel intimidated by seeing like so many like so many papers being published. Noise. People publishing paper left and right, making noise on Twitter and all this stuff. Most of it is really like well, I don't want to be mean, but it's like it's just noise. There's a lot of interest. There's a lot of things to be done. A lot of knowledge, new knowledge to be contributed. Okay, and I feel that we need new mindsets, new generation, I won't say new generation, like even the old generation, new approaches to to solving, to adding new knowledge into these two fields. And most often, I think, like in academia and very often in industry, I personally am seeing a lot of researchers and these things pursuing like this low-hanging fruit type of stuff because they want to publish. The peer review system is like, for me, in my opinion, peer review is broken, right? This pressure of pressuring researchers in academia to publish. This thing is a little bit broken. It's tough. It's for me, it's like it goes against creativity, against so many things. Publish or perish. Yeah, that's exactly. So yeah. So don't feel the thing, because a lot of research, researchers, publishing stuff and these things, they're under pressure, and these things, they're not going to risky ideas, pursuing things that could take like long time, to think, or maybe they're not, lack of confidence to attack big problems. So yeah. So it's definitely, it's the fields, both quantum information and, in physics, theoretical physics, or as a matter of fact, mathematical physics. There is a lot of things that, a lot of people can, there's a lot of stuff new knowledge to be contributed. And maybe this is the thing, a lot of you coming from different backgrounds and these things, maybe, you will have different perspectives, see things in a different way, and, help unlock, because it's like we are like in this stuck. Everything is stuck. We need that the next breakthrough, but it's not happening. In physics, for example, people have been trying so much long trying to, unite general relativity with the quantum mechanics and these things. In fact, does it even make sense to do that? Is there an alternative in these things? All these questions are all like out there. The jury is out. Okay, so Aditya is saying I was very close to taking our degree in maths. Well, you went to computer science instead. Well, it's never too late to to do that, to take a degree in maths. And I also, depending on what you want to do, really, you want to follow academic path, you want to contribute and these things, Okay. Well, I'm glad that all this series have kind of motivated you to regain interest in mathematics. And the mathematics is also a massive, the field is a massive field, as all of you know. And there's so much options to go through. Obviously, for those of you who are interested in quantum stuff, there are certain branches of mathematics that give you the opportunity, that are related, that are obvious kind of things to pursue. But likewise, there might be like other branches of mathematics that people are not have no application in, or it's not obvious that it's being it's applicable or useful in a thing. So yeah, an example is very interesting. Actually, I shared, I think some of you who are I'm connected with on LinkedIn, I shared a book about Simon, who is a hedge fund, Jim Simmons or Simons, depending on how you pronounce it. He was a mathematician, then he became a hedge fund, a quant hedge fund. For those of you who know, Renaissance Technologies, he's the founder of it. Anyway, he and Xinjing Chern, they created this thing called Simon Chern. Well, they didn't call it Simon Chern theory; they call it something else. But that thing was, to do with the differential geometry and differential topology and these things. Nothing to do with physics. Later, people in string theory and other branches of physics, found that it's actually very interesting theory. So, it's what I wanted to say is that mathematics, gives you a lot of options. Really, there's a lot of interesting things you can pursue mathematics for its own sake, but there's also the option that you pursue it because you want to find some interesting ideas that you want to apply, try out. So. So is there any other question? I feel like I'm just blah, blah, blah. It's kind of, I'm running out of things to say because I wasn't planning to say. I'm not sure. I wasn't sure if a lot of you would be hanging around anyway. So unless one thing we can do is if somebody wants me to bring them on the thing to make a comment or something, a general commentary, whatever, I can bring you up. If not, maybe we can leave it here. It's up to you. Because I ran out of things to say. Okay. Well, Barry, you want to make any comment about the thing, the overall thing about the community and these things, or someone else? Yes, motivation is very important. Indeed, especially in these, in the given the current circumstances, right? And for me personally, actually, this is the thing. It's been like a pleasure to be like engaging with you guys. Because outside you, especially with this lockdown, being alone and all this, the thing, I deal with my colleagues. That's it. So having this like extra is like it's been very very good for me. So it's like, I would say it's like a therapy also, a kind of extra thing to occupy my mind in these things. So from that point of view, I would also say thank you to all of you, those who are attending now and those who are watching on YouTube. So yes, math is beautiful. It takes a lot of practice, but it's great when you finally, when you finally understand. This is the thing. A lot of people are like afraid. I think a lot of people that could be very good at mathematics, they get put off because maybe the perception they have of mathematics is completely wrong. For example, I particularly from my experience, I find it the perception that people think about mathematics is all numbers, calculations, and all this blah blah blah. It's all about that. No. That's actually very far from actually how mathematics, especially higher level mathematics, is done. Really, So it's not just about formulas, memorizing stuff, and these things. So often when you talk to people, especially at the earliest at the school level, high school, and these things level, they get scared because that's why I'm probably in favor of reforming high schools. Maybe to start introducing a bit of, I won't say the axiomatic approach to to young people to see it's not just there is a constructive thing in mathematics. It's like it's a very constructive. It's a very I even lost the word. I wanted to say but it's not. It's nothing to do with the what people say, all this, it's all about, calculations and all this and these things. Yeah, okay, maybe if you are doing number theory and these things, even then, you're probably spending more time trying to prove general theorems as opposed to, focusing on, doing concrete calculations and these things. So, yeah. What does the PM stand for? Well, thank you. Prime Minister. Well, I'm not sure if nowadays I really want to be a politician. It's not, it's not maybe different type of politicians. I don't know the thing. It's not a good environment. Maybe in a few years' time. I don't know. I mean, we are all affected by politics, right? So, which is why it's important for us to exercise our democratic power, right? The vote that we have to, to elect people that we, are aligned to what we stand for and these things. So, yeah. Anyway, this is getting a little bit into politics that I don't want to go to. So I guess we leave it here because I don't have anything additional to add because I was expecting anyone else would be sticking around. Only that, yeah, I hope, maybe there should be some sort of a nomination in these things, George, for, yeah. But I'm not sure if I would be become a politician. I would probably not be a career politician type of person. So, yeah. So thank you, Soham. I don't see any other problem. I don't want to stick people around. So yeah, maybe we end it here, and yeah, we catch up next week. Hopefully, we'll have some more interesting stuff to share. Yeah, it's a pleasure to be with all you guys. Thank you so much. And thank you to our friend Soham. And see you next week. Bye, everyone.